Hi students, in this lecture, first I am going to discuss current density. Let us see how it is defined. So before going to discuss current density, first we are going to discuss average current density. Suppose this is the cross section ds, or you can take it as delta s. It is delta s. Through this cross section, a current is passing, that is now delta a, which is a normal to the cross section. In that case, we define average current density as delta I by delta S. This is definition for average current density. After having this, now we define current density as limit delta S tends to 0, delta I by delta S. It is almost same as first we discussed average current, then we have discussed current, right? In the same way, first we are defining average current density, then we are defining current density. So which is equal to di by ds, right? Okay. So here we have taken that current is passing normal to the cross section, right? Now see here. First of all, see units for current density. You can guess from here current, and this is area. That means ampere per meter square. And if you want dimension formula for ampere, it is only per meter square. Meter square means it is L, right? L power minus 2, right? It's a very simple one. For example, we are taking a cross section area and current is now distributing not uniformly. Current is distributing uniformly on the entire cross section and normal to the cross section. Current is distributing uniformly and normal to cross section. Then we can write current density as current by the corresponding area. So in fact, this is nothing but average current density, but distribution of current is uniform. Therefore, average current density and current density both are same. It is just like if velocity is a constant, then velocity and average velocity both are same. Okay, right. For example, current is not normal to the cross section. Let us take this is now the cross section area. Current is passing now like this in this direction of current. But this is now direction of the area vector. Direction of area vector. Okay. This is now delta I. Let us take between these two directions angle is theta. Then we can write that average current density delta I by delta S cos theta. That means we are taking now component of area vector. What is ds cos theta? Component of area vector along the direction of current. Then this is now average current density. In this, if you take theta value 0, then we get same thing here. This is delta I by delta S. So this is now general one, right? Next, suppose we want to calculate a current, how much current is passing through the cross section. Then see what we can write. From definition of current density, di is equal to j bar dot ds bar. J bar dot ds bar. This is giving us a current passing through a small cross section area. This is current passing through a small cross section area, that is a ds bar. Like this, we take all small cross sections, then we have to add up all those things to get current passing through that entire cross section area. That is, we have to integrate. Therefore, I equal to integral j bar dot ds bar. J bar dot ds bar. Okay. Like this, we can calculate a current if we are given how current density distributes across the cross section. Right. Let us see one the points till now what we have discussed. So first one, definition of average current density. Next, current density at a point. So why it is at a point means because we are taking area very small. Delta S tends to 0. Okay. So it is a value from point to point. Or you can say this is now microscopic. Whereas a current in a conductor, it is macroscopic. Okay. Or you can take like this. Suppose we are taking a conductor where cross section is not uniform. This is a conducting wire. Cross section is not uniform. Throughout this conductor, current is now I. Means current is not depending on cross section area. But if you take current density at this point and a current density at this point, both are not same. Because here cross section area is now small. Therefore, let us say this is A and this is B. So current density at A is greater than current density at B. But current throughout the conductor is the same. It is not depending on the cross-section area. So this is a macroscopic property, but J is now microscopic property. Okay, right. Now see next point. Direction of current density is the direction of current means if charges are positive along the motion of positive charges, if charges are negative opposite to motion of negative charge. Okay. And next we have discussed if current distributes uniformly over an area and normal to that, then J equal to I by S. And next, if normal to the area makes an angle theta with the direction of current, then current density is simply taking the component of area vector along the direction of current. Okay. This is what we have discussed regarding current density. See next one, drift velocity. Let us see what it means. So we have discussed that in electrostatics, inside a conductor, field is zero. The reason is that if a field is not zero, electric force acts on electrons. Therefore, because of that force, they will move. But we have discussed like they are not moving. That's why electric field must be zero. Okay. But if you're taking any conductor, electrons inside they move randomly in all directions because of the temperature. And because of this random motion, there is no current. Let us see how to justify this. How to justify this? Let us consider a bulb. Now connect this one to a conducting wire like this. Take a one conducting wire. join the two ends of the wire to the bulb. We can see that bulb does not glow, even though electrons moving in the wire randomly in all directions. So this indicates that random motion of electrons do not contribute to the current because we have defined current as the rate of flow of net charge. That means if you are taking now electrons flowing in one direction, let us say from left to right, and some electrons moving from right to left, number of electrons from left to right and number of electrons from right to left will be same. Then net charge crossing the any cross section will be zero. That means I equal to zero. This is what we can conclude. So random motion of electrons do not contribute to the current. Okay. Now what we are doing is assume that we include one battery. Take a one battery here. I'm taking symbol as it is some B dash. Okay. Symbol for battery. When we connect a battery, we can see that a bulb glows. It indicates when battery is inserted, current is flowing in the wires. Because of that, bulb is glowing. Now see here what exactly happened. So when there is a battery, I'm taking a wire here. For example, this is a conducting wire. And because of battery, one end is becoming high potential and one becomes low potential. This is high potential and this is low potential. That means electric field is now from high potential to low potential. Because of this electric field, electrons will move opposite to electric field. Already electrons having random motion because of temperature. Now additionally because of this electric field, they are moving opposite to field. And when they are moving, they make collisions with the positive ions. So whenever they are making collisions with the positive ions, they lose energy and again they start moving because of electric force. So this process continues. And if you take on an average, what happens is for electrons, there is no net acceleration. For electrons, there is no net acceleration and they move with a constant velocity. And that velocity is known as a drift velocity. They move with a constant velocity known as drift velocity. And let us see how to calculate that. So velocity of electron is given by acceleration is, or if you want to generalize, take charges Q, electric field E, then force is Q into E, force by mass, acceleration at time t, velocity equal to acceleration to time, right? Now, if you take average value of velocity for all electrons, not for one electron, average value of velocity for all electrons. So since acceleration is a constant, remaining is now average value of t, and that becomes now relaxation time. I am writing here q e by m into relaxation time. So relaxation time means it is the average time between two successive collisions. This is now expression for drift velocity. Okay. Let us see now some points regarding this. So in electrostatic conditions, electric field is zero everywhere inside the conductor and there is no current. However, this does not mean that all charges within the conductor are at rest. The reason is they move randomly in all directions because of temperature and this does not contribute to current. Okay, and see diagram here carefully. When there is no electric field, path will be the dotted line, sorry, solid lines colliding here, then moving like this, again collision, moving like this, again collision, moving like this, Again collision, moving lag is reaching point X. So sorry, reaching point Y. So moving from X to Y by making six collisions. Okay, one, two, three, four, five, six. Now, if we apply electric field, the path will be now shown here by dotted lines. In fact, path is somewhat parabolic, and we can see here finally what happened. Instead of reaching point Y, it is now reaching point Y dash. So you can see clearly there is a displacement opposite to electric field. Electric field is left side, but displacement is now right side. There is a small displacement. Okay. This is because of the drift velocity, right? Okay. Next we can see mobility. Mobility of charge carriers is defined as drift velocity of charge carrier per unit electric field. So simply divide with electric field. Okay. And we can see units here. Units and dimension formula. Let us now derive once. Given meter square volt inverse. See once units and dimension formula. Given mu value, drift velocity upon electric field. Velocity means meter per second. This is electric field. Electric field means potential difference by separation, right? Potential difference, it is volt. By separation means it is length, meter. This is now meter square, volt inverse, second inverse. Okay. And if you want dimensional formula, see what we can write. Dimensional formula. Let us consider F bar equal to Q into E bar. So dimensional formula we can write for mu. Velocity. Velocity means meter per second. Okay. In the place of electric field, I can write force by charge. Force means mlt power minus 2. By charge, charge means ampere into time. Okay. That's what we get. Time gets cancelled. Next, what else? L and L gets cancelled. Remaining is now m power minus 1, t power minus 2, a power 1. Like this, we can derive dimension formula on the spot. Okay. Let's check once what we have derived and what is given here. Velocity, meter per second. This is now charge, ampere into time. Force is m L t power minus 2. Right? M power minus 1, L cancels, so L power 0. T power minus 1 cancel. Remaining is now t power minus 2 becomes t power 2. Okay. T power 2, a power 1. Okay. Right. Let us now get relation between current density and drift velocity. And after that, we discuss Ohm's law, that is relation between J and E. Okay. See, first one, current density and drift velocity. We can see here relation between current density and drift velocity, right? See how to get it. Let us consider a small time interval dt. This is now one conducting wire. In a small time interval dt, electrons will move at distance that is given by Vd into dt. It is small time interval dt. Suppose this cross section area is equal to 8. then into area. So this gives us a volume, right? Drift velocity into dt, that is now length into cross section area. This gives us volume. Let us take now n stands for number of free electrons per unit volume. So I'm taking into n. This is volume. This is now number of free electrons per unit volume. This is giving us charge. Charge confined to that volume. Okay. This is now dq. dq. Okay. So if you want to find the current, I is now dq by dt. I is dq by dt, that is equal to dq by dt. How much we get? N into, wait. Here actually we have to multiply with the charge of electron. Or if you want to generalize, take charge as a q. Okay. Then n q drift velocity into area, right? After having current, now you can see here I by A. I by A means if you assume that current is now normal to the cross section area, if you assume current is normal to cross section area, then directly I by A and distribution is now uniform. Distribution is uniform. Then I by A gives, this is actually average current density. Since we are taking distribution of current is uniform and normal to cross section, this is also equal to current density. Okay, that is equal to n q into drift velocity. So we got now relation between current density, that is j bar equal to n into q into drift velocity. Now see carefully. Suppose charge is a positive, then velocity will be along electric field. Or you can say n is a positive number, charge positive means direction of j bar is direction of drift velocity. If charge is negative, direction of j bar will be opposite to that of drift velocity. Okay, right. Now see, just now we have discussed relation between a drift velocity, right? Drift velocity is acceleration is force by mass into relaxation time, right? See from this what we get? N q square n q square e by mass into, wait, this is n q square e by mass. You're having into tau, right? Into tau. Or from this, what I can say is j equal to some constant. What is it? Some constant. That is now sigma into e. So we are saying some constant means that term here, sigma n q square tau by mass must be a constant, right? So if you are taking at a given temperature, J bar is a proportional to E bar at a given temperature. And that result is known as Ohm's law. That means at a given temperature, sigma is a constant, where sigma is known as electrical conductivity. It is known as electrical conductivity. Electrical conductivity. And reciprocal of this is known as resistivity. Reciprocal of this is known as resistivity. That means at a given temperature, this relaxation time must be constant because charge of electron constant, number of free electrons per unit volume constant, mass of electron constant. Means at a given temperature, if relaxation time is a constant, then we can say J bar proportional to E bar. So we are saying that at a given temperature, for a conductor, J bar proportional to E bar. This is known as Ohm's law in terms of J bar and E bar. Or we can say Ohm's law at microscopic level because we define J value from point to point. This is microscopic level. Okay. Next, see what else here. So we got relation between current density and drift velocity and relation between J bar and E bar, right? So next one is the calculation of resistance. See how to get it. Calculation of resistance. So we got now J equal to sigma into E, right? Modulus values. And I will write here J value how much, sigma value how much we got. Or let us take J equal to how much we got N into Q into drift velocity. In the place of drift velocity, we have taken force by mass, acceleration into relaxation time, right? So in that we got N Q square tau by mass into E. Okay. Now I am writing here. Let us take a conducting wire of length L. Okay. Across the ends, potential difference equal to V. Okay. Since the field is uniform inside the wire, we can write E value. It is equal to V by M. Since the field is uniform. Substitute values here in the place of G. Current by area, that is equal to in the place of sigma. Or simply take sigma only. It is sigma. In the place of E, writing V by L. Now from this, see what we get. V equal to it is I by V equal to I by, we are having here A sigma by L, or writing this as I by, or taking this as what you call I into L by A sigma, and 1 by sigma is known as rho. Okay. So it is now rho L by A. So V equal to I into R, where R is known as electric resistance. R is known as electric resistance. So R equal to rho L by A. So rho is known as resistivity and L is length of conductor and A is known as cross section area. Okay. So at a given temperature, R is a constant. So when R is a constant, V proportional to Y, or you can say I proportional to V, because if more potential difference, we get more current. So I proportional to V at a given temperature means R is a constant. R constant means resistivity is a constant, means sigma is a constant. Sigma constant means the relaxation time is a constant because remaining are constants. Okay. So this is what we are going to use for solving problems. Okay. And focus here how to get the value of A and L. Right. Suppose we are taking now a cuboid. We are taking one cuboid. Let us take length is L. There's a height is H. Breadth is B. Okay. If current flows like this, then L means it is length. Okay. And area means we have to focus now this cross section area. Okay. Suppose I'm taking current flows like this. If a current flows like this, then H becomes this length. Okay. Then this cross section area will be A. That means in which direction current is flowing. Accordingly, the values of L and A change. In this, if current flows from left to right, this is L. This is now cross section area. That means it becomes now B into H, right? If current flows from top to bottom like this, H becomes length and area becomes now, this is the area which is equal to L into B. So we should be very careful while calculating resistance.